Yeah. So fine. So welcome back to the course. This is analog VLSI design. This is an NPTEL MOOC course. The instructor for this course is Dr. Imran Mandal. He is a professor in IIT Kanpur in the electrical engineering department. Myself, I am Mayank Anupam. I am the tutor for this course. I wrote these tutorial sessions. So I am also a PhD student and from IIT Kanpur. So fine. So yeah, so this week, so today we will be discussing whatever was covered in week 9. So in week 9 uh, we saw how do we use pMOS, right? So we got introduced with the pMOS thing, pMOSFETs for the first time. Then we saw how to use it. We also learned a little bit about how the pMOS actually works on a device level, and so how to use it to design circuits and all. What is the incremental model? How do we design a small signal model for it, and all those things. So after that, we saw how to build a common source amplifier with a pMOS flow, right? We also saw some other circuits also with pMOS. So in the assignment for week 9 also, you must have seen all the circuits are for pMOS only, right? So today we'll be solving a couple of problems which will help you understand how to deal with pMOS and NMOS both when you have them in the circuit. Fine. So do you have any doubt first of all in the content that was covered this week? Any doubt theory wise, or any other problem? Okay, so that is fine. I don't have much to. I don't have anything here to say in the summary itself because I think everything was covered in the lectures. Let's start straight away with the questions. Fine. So this is the first question. So I would like you guys to try today, okay, with me. I'd like this class to be a little bit interactive today because today I want to. So today will be a lot of learning about designing and all. So today I would like you to. I would encourage you to actually participate in the discussions. Fine. So this in this question we see there is a pMOS here. M2 is a pMOS, M1 is a NMOS, right? And this is how we have given the circuit. This is how we have biased the circuit, right? And this biasing is not shown here. VB2 biasing is not shown, so that we will discuss later. Anyway, so this is how it is. Mu and Cox, all these parameters are given for this. Please note that the threshold voltage here for NMOS transistor is 1 volt, and for PMOS transistor threshold voltage is taken as minus 1 volt. So here I'm just taking the magnitude of it. So it's 1 volt. Is that fine? So that is fine. Mu p Cox, you can see that you must have also learned that mobility of holes is approximately 2 or 2.5 times lower than the mobility of electrons, right? That is why you see this difference here, right? You can see mu and Cox is 100, whereas mu p Cox is 50. That's fine. Now, okay, there is a slight problem here. This is 40, this is 20. And to take care of that mobility difference, we have sized our pMOS slightly larger, okay, compared to NMOS. So you will come to appreciate this just in a short while. Fine. This is the bias voltage VB1, 2 volts, VDD is 4 volts. So the first question is, what should be VB2 for all transistors to be in saturation? Okay, so tell me, how do I proceed with this question?
Sir, you have told that W by L M2 for W by L ratio is for M2 is 40. The reason, please repeat the reason, sir.
Oh, so I was under the impression that this is covered. So fine. So this is the mobility of so mu p Cox, this factor, right? Is you can see that it is 2 times lower, right?
Okay.
Mobility of holes is 2 times lower than mobility of electrons, correct?
Okay.
So to make sure that the current, so you know that in the saturation the current
Yes.
equation is mu p Cox into W by L, right? Something like
Yes,
that.
yes. Got it, sir.
Got
Got
it.
it.
Fine, fine.
Got it.
Thank you.
Got it.
Good. All right. So now tell me, uh, what should be VB2 for all transistors to be in saturation? So how do I proceed with this question? What should I do here?
Actually, we need to consider that equation Vd less than or equal to Vg
Yeah. So
plus Vt.
let's do that. So this is V out, okay, or VO in short, right? So this is the equation. So what for saturation? Is that correct? Any comments you would like to make here? The first question that I would like to ask you is, why do you think I have used modulus everywhere? Why have I used mod everywhere? What you
This
say?
is for M2, right?
No, for everyone, for M1 or M2. Yeah, so this is modulus because you can see that for M1 it doesn't matter, right? If for M1 VD is greater than VS, right? VDS will be positive, VGS will be positive, VTH will be positive for M1, right? So if I want to elaborate on it, for NMOS, that is M1, how will it look like? VDS greater than VGS minus VTH, right? Because all quantities are greater than 0. Am I correct or not?
Yes.
Yeah. And for pMOS, how will it look like? This will be minus
Minus
VDS
VDS
greater
minus
than
VG
minus VGS minus
VTH.
VTH P, right? VTH. Fine. Am I correct? So just ignore this. So let it be in mod plus only. This is fine. So how will this become? This become VSD greater than VSG minus mod of VTHP. Is that correct or not?
Yes.
Yeah. So
Uh,
so
you should use minus VTHP right there if you want to change the sign on the next side.
yeah, it can be, but I don't want to because I've already used it here like this. So I don't want to do that.
Okay.
Yeah, fine. So this is fine, right? So that is why I've used a common symbol for both of them. So common notation for both of them would be like this, right? I simply use modulus. So remember this, okay? Remember this. You do not need to remember separate conditions for PMOS and NMOS. Just remember that you just have to use modulus everywhere. Okay, then that way you will not forget this. All right, fine. So this is the condition for saturation, right? Now tell me, what do I do? So this is the condition for saturation. So how will it look like for both of them? So for M1 it will look like VO. VD is what? VO, right? VS is 0. So this is greater than. VG is how much? VG is how much? So just ignore for time being that VI is there. So I'm talking about bias condition, so Vi can be ignored now. VB1 is the one, right? VG. So VB1 minus VTHN. And how will it look like for pMOS? Put it here. For pMOS, how will it look like? It will be VDD minus Vout should be greater than VDD minus VB2 minus VTHP. Correct? Okay. So first of all, let us simplify it. So this is not, there is no need to simplify this because this is already the simplest that I could get. What is VB1 by the way? VB1 we know, right? 2 volts. 2. And what is VTHN? It is 1. 2 minus 1. And how will it look like here? So VDD and VDD cancel each other. And just put everything here. Okay. So your VO should be less than equal to VB2 plus 1 volt. Correct? Isn't it? Now tell me, what do I do? Now do I have anything in else that I can do? So how will I find out V out? I need some way to relate. So V out has to be greater than equal to 1 volt. So that much I know. So so this guy, so V out has to be greater than equal to 1 volt. That much I know. So if I use this inequality in here, so what will I get? So this guy V out has to be greater than equal to 1 volt, but it has to also be less than equal to VB2 plus 1 volt, right? So now tell me, how do I find out? What do I do now? What do I do now? Any ideas? Yes, someone?
Like
Hmm. Yeah, go on.
VSG should be greater than V threshold.
No, that is by default we assume. So don't worry about cutoff. Okay. So that is fine. VSG should be greater than cutoff, so that is fine. Yeah, that's actually a correct point for VB2. Yes. Okay, so let's take that also. So for cutoff VSG, or other VSG M2 should be what? Should be greater than equal to mod of VTHP. So from here you will get what? VDD minus VB2 should be greater than equal to 1 volt. So VB2 should be less than equal to 4 minus 1 is 3 volts, right? 4 minus 1 is 3 volt. So this is fine. So this is our equation 1 and this is equation number 2. Now tell me, what should I do now? What do you think should we do?
You can take directly VB2 as 3 volts
Why should I do that?
in order to be in saturation.
Okay, so let's take VB2 is equal to 3 volts and see what happens. Let us see what happens. Okay, so let's take VB2 is equal to 3 volts. So definitely this condition is not violated, right? VB2 is 3 volts, so VO is less than 4 volts, so that's fine. So the condition would be VO should be less than 4 volts, so that is fine. Now let us try to see what happens if we take VB2 is equal to 3 volts. So now let's think in terms of the current. So let's find out what is the current. So Excuse me 1 second, please. Okay. So what is the current now for M1? So tell me if you find out the current for M1. So let's call it. Let's call this current as. Let's copy this. Hmm. So let's call this current as I1. Let's call this current as I2. Okay. So what is I1? What is I1?
Half mu MCox W.
Mu n mu n C ox by 2 W by L of 1 times VGS minus VTH n whole square. Correct? How much will that be? Mu n C ox is how much? 100, right? So 0.1 milli divided by 2 into W by L1 is 20 into VGS minus VTH is how much? This is 2 minus 1, so it is 1 actually. 1 the whole square. That will become how much? 10 into 0.1 is 1 milli, right? 1 milliamperes, right? I1 is 1 milliampere. Now M2 is also in saturation, right? So now tell me, if M2 is in saturation, what is I2?
Question should be on in the other way, right? If I2 is 1 milliamp, then what should be the?
No, I want you to focus in this way only. So tell me,
Okay.
by the way, what will be I2? VSG minus VTHP,
VTHP whole square.
right? Fine. So tell me what will be I2 in that case. So mu PC ox is how much? 50, or rather 0.05 by 2, and W this is 40. VSG is how much? You said that VB2 has to be, so VSG is VDD minus VB2 minus 1, right? So how much will this be? 0.05 divided by 2 into 40. So this is 4 minus 3 is 1, 1 minus 1 is 0. So this is 0, right? This looks like the current is 0 here. Yes. So Nikhil, I think you said, right, that VB2 can be taken as 3 volts.
Yes, I think at the edge of saturation we should not bias.
Yeah. So tell me what should it be? First of all, let's say it is anything else. So let's say VB2 was not 3. Let's take it as 2.5 volts. That is also perfectly acceptable, right? 2.5 is perfectly acceptable, isn't it?
Yes.
Yeah. So tell me what will happen in that case if it is 2.5. So VDD minus 2.5. So 4 minus 2.5 is 1.5 minus 1. How much will that be?
1 by 2.
0.5, right?
Yes.
0.5 the whole square. So 0.05 divided by 2 into 40 into 1 by 4. Correct? So this is 10, and 10 into 0.05 is 0.5 by 2. So 0.25 milliamps. Yes. Now do you see a problem here?
Both should be equal, I guess. I2 and I1.
Yeah. Why should they be equal?
Uh, why? Because these drains are connected, right?
Yeah,
Of,
drains are
and
connected. So what?
Yeah, so M2 is basically acting as a active load here, right?
No, no. Yeah.
for
Okay, fine. So
for
it is acting
for
as active load.
PMOS current flows from this, right?
Yeah.
What you
So
call source to drain, and for
yeah.
NMOS
So
drain to source.
this is flowing like this. This is flowing like this, right? So
Yes.
Yeah.
so remember, like in last class, I think Nikhil was asking me, right? Or I don't know who was asking me about MOSFETs. How can we? What is the best way to model a MOSFET? So I said that in a common source configuration, it acts like a voltage controlled current source. Sorry, right? I said that. Is my screen visible still?
No.
No.
Okay, 1 second. Something happened. Yeah, now it is fine, right? Yes, now it is visible, right?
Yes.
Yeah. So yeah. So last class I remember some Nikhil asked me that what is the so this basically I said that a MOSFET acts like a voltage controlled current source, right? Where it is used in common source configuration, isn't it? If you remember. So at the very core of it, that the situation from drain to source, how does it look like? I mean, it looks like it is a current source, isn't it? Between drain and source. So what I'm saying is, yeah. So uh, how does it look like? Basically between drain and source. So here it looks like it is a current source, right? Here also it looks like it is a current source. Am I correct or not?
Yes.
Yeah. So now tell me, if these are basically two current sources who are competing with each other, right? So as one of you rightly, as you have rightly pointed out, the current should have been same here, right? 1 milliampere and 0.25. They are different currents. But so what happens if their currents are different? What happens if the currents are different?
The final one will prevail, I think.
So so this is how much? 0.25 milliampere. So this is 1 milliampere. What happens if the two current sources are different and they're connected in series? So these two current sources are connected in series, right? Isn't it?
Yes.
Yeah. So to be very clear, this is one current source. This is another current source. This is VDD. This is 1 milli. This is 0.25, and this is 1 milliampere. So what happens? What is the problem here? Can this ever happen?
Actually, in series, I guess current should be same.
Yeah, current should be same, but let's say I take one current source, I take another current source, both are of different values, and I short them together in series. So what is going to happen?
So I think it will be 0.25 amp, not more than that.
No. So how will it be? How will it happen? This current source does not know anything, right? We know that a current source has a property that it will. Sandeep, please mute yourself. Um,
So what I understand about that, if you let's say you have a 1 milliamp source, and the circuit after that source will get the 1 milliamp current, and before 1 milliamp all other thing will be 0.25 amp.
okay, okay. So let's look at it another in this manner. So. mm You remember that in I don't know how many of you have tried this blender at your home. People always say that, oh, you must have always heard that something is short circuited, right? in the home, right? Sometimes there is overload, something is short circuited, there is some problem, right? Things get burned. That is not good. In electrical appliances, right? You know that short circuit is always a bad thing. Why? What do you mean when things when we say that something is short circuited? There is a power
Like
source. There is a power
two
source.
terminals are connected to same thing.
Yeah, so there is a power source, right? It was supposed to go through a load and then to the ground, right? Something like this was supposed to happen, but what ended up happening was, because of something, this guy got connected to this, right? So this is a short circuit condition, isn't it? Are you guys with me?
Yes, yes.
Yeah. So this is short circuit condition. So what happens in this condition? Why is this a problem? If you are touching it, what is going to happen to you?
Actually, the impedance might be zero, such that's why current will be infinite.
Yeah, current will be extremely large, right? Not infinite in practical appliances, because here there will be some impedance for this device also, right? So not infinite, but it will be very large, right? A large current will suddenly flow, and which can completely destroy your device, right? Which can completely destroy your device completely, right? Something will burn somewhere. It's not good. So tell me, why was there a very large amount of current? Because voltage is here, sorry, because this voltage here, it only knows one thing, right? That it has to maintain a certain voltage in here across it. But when it gets connected to ground, ground knows one thing, that it has to maintain 0 volt there, right? It is like connecting two voltage sources. So this is 0 volt, this is, let's say, 200 volts. So if you connect both of these like this, what is going to happen? Something really unholy is going to happen, right? A lot of current will flow, and something weird will happen here, right? So it is not a good thing when you connect two voltage sources, both of which are trying to maintain their own so these are two kings fighting each other, right? Both of them are trying to establish their own rule, but who ends up winning, we don't know. Something and all will happen, a war will happen, and things will simply die. This is not good. So similarly, uh, in when two current sources are placed in series with each other, they are also going to fight, okay, if the currents are not same. Tell me what is going to happen now, if since I have talked so much about voltage sources, tell me what is going to happen when we connect two current sources with each other like this here. Yes, anyone, please? So just as in this condition where two voltage sources were placed parallel to each other and they were different and a large current flowed through it, similarly, if the two current sources are placed in series with each other in this situation, and both of them have different currents, what is going to happen is, suddenly this voltage here, which is exactly in the middle here, this voltage will suddenly rise or fall. So what is going to happen here? So from the top, it is giving 0.25 milliamperes. At the bottom, it is supposed to it is demanding 1 milliampere. So what is going to happen to this node voltage? It is suddenly going to go down, right? It's going to drop, isn't that? I mean, are you guys following me?
Yes.
Hmm. So this voltage here, this is suddenly going to go down, and it's, if it is an ideal condition, this voltage will go all the way to infinity, minus infinity, sorry. Okay. However, so that is why two current sources which are placed in series with each other cannot have two different currents, okay? Because then the voltage will suddenly go up or down based on what is happening. So this will suddenly go to minus infinity. But in real circuits, that is not possible, right? There is no because no voltage can go to minus infinity practical circuits. So what is going to happen here? What is going to happen in here? What is this voltage going to go to suddenly because of this mismatch in voltage currents? What is V0 going to become?
minus infinity.
No, at this place, I'm talking about a circuit. It is a practical circuit, right? It cannot go to minus infinity here. Here it will go to simply 0 volts, right? Not even 0 volts. It will go to a lower value, and it will go to a value till it will go to a value. It will start going down, right? The voltage V naught, it will start going down till what point? It will start going down to the point where the transistors are no longer in saturation. Okay, it will start going down to the point where M1 is no longer in saturation. So the moment M1 is no longer in saturation, the current equation will be different, right? The current will start to reduce after that. As the V naught is going down, the current will start going down, and then at a point will come where this current and this current will become equal. Are you following me?
So Mayank here, here V naught will go like initial like below that minimum like VD value, VD greater than equal to VG minus
Yes, it
VTH.
has to go down, right? Because see, right now the currents are such that they do not even depend upon V0 value, right? Because this is in saturation. The currents only depend upon VB2 and VB1, isn't it? And we see that because of the difference in the because the values were taken such that there was a difference in the current itself. Assuming this is in saturation, what will happen? Currents cannot be different, right? In the same branch, the currents cannot be different. So that is why this voltage V naught here, it will start to go down. It will start decreasing. It will start decreasing, and it will decrease to the point where V naught is less than VD sat of M1. The moment that happens, the current will then start decreasing, right? For M1. You get my point? Because now since the M1 transistor is in linear region, so okay, let me write it. So VO will decrease such that M1 goes out of saturation, right? And then which implies VO, sorry, IM1 or I1, so this is I2, this is I1. I1 will also start decreasing with V0 to the point where I2, sorry, I1 equals I2. Get my point? Are you guys understanding me?
Yes.
Yeah, so I hope there is no doubt here, right? This is a very important point. This is
Up
the
to which point it will decrease?
yeah, that's what na I told na it will decrease to the point where I1 becomes equal to I2.
Okay.
So
So
that's the yeah. What?
like I2 remains same, but I1
Yeah,
only will
yes.
reduce.
I2 is remaining same because this transistor is not going out of saturation. M2 is not going out of saturation. Which guy is going to go out of saturation? Because see, for M2 to go out of saturation, V0 has to increase, right?
Yes, yes. So
Yeah,
that's why even if it decrease also, it will
yeah,
not affect
yes,
into.
yes. But for M1 to go out of saturation, V naught has to decrease. So when V0 will start decreasing. And why is V0 decreasing, by the way? Why did it not choose to increase? Why is V0 decreasing? Come on, guys. Why is V0 decreasing, not increasing? V0 is decreasing because the current that is being demanded at this node, this is V0,
Like,
right?
like you're supplying less and demanding more.
Ah, right, exactly. Good, very good. So that is the exact way that I would like you to understand. You are supplying less, demanding more. So V0 is going to go down, right? And if it had been the opposite case, that you are supplying more but demanding less, then this would have gone up. Okay. So both of the conditions are not good. So in both of the conditions, when two current sources are fighting with each other, it's going to happen. One of the other cases is going to happen. One of the either cases is going to happen where either the either M2 will go out of saturation or M1 will go out of saturation. Okay, fine. So if that is understood, so now tell me, what should VB2 be for both the transistors to be in saturation? So you said that VB2 can be anything less than 3 volts, right? That is what you said. So we took a voltage which is equal to 2.5 volt. It turns out that this is not good, because in this condition M1 will go out of saturation. So tell me, what should VB2 be?
Like I think we need to make I1, sorry, I mean I2 equal to I1.
Yes, exactly. So how much
Then
is I1? I1 is equal to 1 milliampere. That is given because of the way that we have biased it, right? We have already biased with 2 volts. We have already biased M1 with 2 volts. So that is why I1 is going to remain fixed, right? So the only thing that we have a handle now on is M2 biasing. So VB2 has to be such that M2 also supplies 1 milliampere, isn't it? So isn't it? So in that case, what will be I1? Tell me. So I2 is no I1 is known equal to 1 milliampere. So I2 is how much? This equation, right? So mu p times C ox by 2 W over L to VDD minus VB2 minus mod of VTHP the whole square, correct? So from here, what is VB2 going to be? Okay, let's do it. This is 1 milliampere is equal to 0.05 milli divided by 2 into 40 into 3 minus 1 is 2, 2 minus VB, sorry, 4 minus 3, 1 is 3, VB2 the whole square. So milli and milli cancel with each other. Fine. Amperes also cancel. How much is this going to be? So this is 20. 20 into 0.05 is how much? 1, right? Correct. It is 1, right?
yes,
So it is 3 minus VB2 the whole square is equal to 1. So VB2 is equal to how much? 2, right? 2 volt or 4 volts, right? It is either 2 or 4, right? So which of these two is going to be the correct one? 2 or 4?
2.
Yes,
2.
yes, because otherwise there will be cutoff, right? There will be cutoff condition, right? So we have already seen that VB2 has to be less than 3 volts. So 2 volt is the correct answer. So VB2 has to be 2 volts. You see, in this condition, I actually made it. I simplified it with respect to the channel length modulation thing, right? I assumed the channel modulation to be absent here. However, if you would have assumed channel length modulation here, then it would have been much easier for you to see. See, let's assume.
Mayank,
Yeah.
I have like one score. Like if this increases, right, then like M2 might go into linear region, right?
No, no. If this increases, then not. If this decreases, then M2 will go into linear region. So
Okay.
VB2 has to decrease, right? If for PMOS, the voltage has to gate voltage has to go down for current to increase, right? Because it is VSG, VS minus
Like
VG.
I'm saying, like you have taken it as infinity, right? Minus infinity. Suppose in the case if it increases, then M2 might go what you call out of
Yeah. So
linear, right?
yeah,
In that time,
that's what I'm saying. If this current, the 0.25 milliampere, na, if this would have been, let's say, 1.2 milliamperes, okay.
yes,
So then yes, then it would have gone to plus infinity here, and in this case, at this place, what would have happened? V0 would have
M2
started increasing to the point where M2 goes out of saturation.
out of saturation. Okay,
Yes?
that's what I'm.
Yeah,
Okay. Thank you.
good. So this is a very important point because after this I'm going to come to another point which is also very important. So anyway, so this is VB2 equal to 2. So now let's assume there's some channel modulation. So I know that channel modulation has not been discussed for you for PMOS case, but please understand the channel modulation in PMOS is actually works in exactly the same way as NMOS. Okay, so it doesn't matter. Assume CLM to be present for M1.
Like here also, that will be connected between drain and source.
Yeah, so now see, you will be able to understand it much better. So now the circuit is, this is the circuit, right? Now the situation is, this is RO2, okay, and this is RO1, and this is your V out. Okay, so now tell me, first case where you assume lambda is very large, lambda is very small, sorry, assume lambda is very small. Okay, so what I'm saying is, so let's say now if the currents are different, now let's say the current is different, so how will this model look like in small signal this thing? If I only look towards the drain source thing, so how will this look like? There is a current source here, there is a current source here, then there is R out. Hmm. Then there is another current source here, there is another R out, right? And this is your V out. This was 0.25 milliampere, this was 1 milliampere. So this guy is supplying from the top, it is supplying 0.25, at the bottom it is only it is demanding 1 milliampere. So what is going to happen to this V out node? I mean, here you can precisely say what is going to be the voltage here. What is going to be the voltage here?
Can simply add up the currents
So how much is the difference current? 0.75 milliampere, right? So that much current has to come from where?
from R0 to R0,
Yeah.
R0
So
to
it is
R1.
basically the difference current has to flow through R2, R0 to R1, right?
Yes.
Isn't it? So it will be like this condition. This is the difference current of 0.75 milliamperes, which has to flow through where? RO2 R01, right? So you can see that this voltage will become how much? Will go down, isn't it? This, because you see the sign here, it will start pulling the current from this node. This is what? V out, isn't it? Are you getting my point? Are you getting my point?
Sir, how RO1 will be parallel to RO2, sir?
You see, first of all, this is not a very correct way to draw. Okay, I'll
Okay,
come to your point, but first of all, let me tell you
okay,
something about it.
okay, okay.
See, first of all, this is not a very correct way to draw. I've just shown it for simplicity. You see, the
Okay,
currents
sir.
here. No, no. Let me finish. The currents here are actually what? They are biasing currents, isn't it? They are biasing currents, quiescent currents, correct? So first of all, the current that I've shown here, 0.75, 0.25, 1 milliampere, these currents and this RO2 cannot be together, okay? Please note it. This is not a correct way to draw. I'm just trying to, I've just drawn it for simplicity to understand. So there is some output resistance. The moment something will, if there is a change in current, what is going to happen at this point? The drain voltage will start decreasing, right? The drain voltage will start decreasing, because of which, what is going to happen? Because of channel length modulation, the drain voltage, when it decreases, the current also will start falling down, isn't it? Is that understood? The same thing that I was saying earlier, the same thing is also explained here. Because of the drain voltage that is going down here, V out is going down for M1. It's a drain voltage for M1, right? It will start impacting the current that is being demanded by RO1, right? Sorry, M1. So what will happen when VO goes down? VO is the drain for M1 as well as for M2, right?
Yes.
Yes. So what is going to happen for M2? The drain voltage is going down. So what is going to happen for pMOS? If the drain voltage goes down, the
It does.
current has to increase, right? See, in the pMOS, for pMOS, the current equation for channel modulation with CLM is like this. It is I is equal to, or ID is equal to, half mu N mu P Cox W over L P VSG minus VTHP mod square 1 plus lambda VSD. Okay, got it? For NMOS, you already know, right? It is ID is equal to half mu N Cox W over L N VGS minus VTHN the whole square 1 plus lambda N VDS. So it is very easy to understand now that for a PMOS, if the drain voltage is going down, what is going to happen? The current is
Like
supposed to be increasing, right?
Yes.
Yeah.
like source to drain voltage increases.
Yes, correct. So that is why the current should increase. Also, whereas for the NMOS case, if the drain voltage is going down, then current is supposed to decrease, right? So tell me,
Yes.
isn't that something which we desire, right? You see, because you see, NMOS is actually requiring larger current. It is demanding more current than PMOS could supply. It is demanding 1 milliampere, whereas the PMOS is only supposed to give 0.25 milliampere. So what is going to happen? It is going to tell the drain that please go down. The drain starts to go down, and the current that NMOS requires starts to come down. Whereas at the same time, the current that PMOS is giving, current that PMOS is supplying, it starts to increase, right? So one level starts to increase, one level starts to decrease, and this will keep happening until both the levels are in sync. You get my point?
Yes.
Yeah. So exactly this is what I'm trying to explain. So I hope that is fine. remove this because this is not the correct way to write it. Even this is not correct anyway. Okay, good. So now that we have very well understood this point, now you will be able to appreciate the next question. So we now know that VB2 can be, VB2 has to be equal to 2 volts, and in that condition the currents will be same and nothing will be, there will be no problem, right? So the second question is regarding that only. Second question is, one second. Hmm. Yeah. So yeah, so now we have successfully established that this is 1 milliampere, this is also 1 milliampere, and this happens when VB2 is equal to 2 volts and VB1 is equal to also 2 volts. Fine, this is something which we know. Now let's say because of some reason, I don't know, and how will you generate VB2, by the way?
Mayank, once can you show that question, second one?
Yeah, so I was anyway going to say that. Okay, but anyway, second question is here.
Like for that you have said with what you call uh, with CLM, right? So there just we need to equate those two currents, right?
Yes, you have to equate those two currents and see where does that take you, what will be
Like
the
we need
VDS
to
value.
VD like that value V not.
Yes, and see
Okay,
whether after that the V naught value that you get, whether that still makes the two circuits be in saturation, or whether it takes them out of saturation. Okay.
okay, okay.
Okay. Anyway, so I was saying that how will you give VB2, by the way? You just connect it with a voltage source, right? For time being. So ultimately, when you will design it, you will need a resistor divider like this. But for now, just assume there is a voltage source here. So that's voltage source here, which is 2 volts. Okay, so this is how you design it. So now tell me, yeah, in this condition everything is fine, everything is good. Now tell me something. Due to some reason, mod of VTHP, it let's say it decreases. Okay, due to some reason, mod of VTHP decreases suddenly. VTHN remains same, but VTHP decreases. Uh, so do you want me to discuss the assignments? Vimal, okay. So I cannot discuss the assignments. That's what. So I cannot discuss week 9 assignment because the solutions I think are not uploaded yet. We are not allowed to discuss the assignments that you have to do yourself. What I can do is simply give you hints or maybe help you out if you are not able to understand something, but I cannot give you the solutions for them. Yeah. So what? Let me finish this first. I will come to that. Yes. Fine. Tell me, what about the yeah. So let's say VTHN remains the same. However, the this VTHP, it suddenly decreases. What is going to happen? What is going?
M2 will increase the current.
Yeah, M2 will increase the current, correct. M2 current will suddenly increase. So let's say this current increase. So this is the way that I will show it. So it was, let's say earlier it was like this. Now it will
M2
increase.
might go into like go out of saturation also.
Yes. So again the same thing, right? M1 is demanding this much of current. Earlier M1 was demanding this much current. Now the current of M1 the current demand of M1 is still the same, whereas M2's current supply is suddenly increased, right? So that will simply mean that V0 will start to go up, isn't it?
Yes.
V0 will increase. Till what point will it increase? Come on, tell me. I've spoken a lot on this and I wanted to answer now. So V0 will increase, that is known. Till when will it increase?
Till M2 reduces the current.
Yeah, so when will it start reducing the current? So the VGS is not changing, right? For M2 VSG is not changing. How will the current reduce?
Like I mean, M2 might go into linear region, then it
Yes,
might reduce.
yes, exactly. So once it goes into linear region, then the current not only depends upon the VSG, but it also starts to depend upon VSD, right?
Mayank, here, like you said, threshold voltage decreases, then both currents should decrease, right?
No, no, I have only said that
Okay,
threshold VTHP decreases.
okay, P, okay. Thank you.
Yes. So one second. Yes. So got it right? The moment M2 will go into linear region, the current that M2 is supplying is not only dependent upon VSG of the M2, but it also starts depending upon the VSD of the M2, right? It also starts depending upon the drain voltage. So after that, if the drain voltage increases, it will start going down, right? The current will start decreasing. Yes. So this is I2, this is I1.
Like I2 might increase, then again it will decrease to 1 milliamp here.
No, no, it will start decreasing. Uh, yeah, sorry, it will start decreasing and it will decrease to 1 milliampere, right?
Okay.
So basically, you were trying to say that I2 will increase till the boundary, and then it start decreasing, right?
It will first increase because suddenly VTHP is changing, VTHP
Yeah.
reduced, so it will suddenly decrease, right? Sorry, suddenly it will
Yeah.
increase, and then it
Yes.
will start decreasing because the current demand is actually lesser, right?
Yeah.
Now,
So basically, if it is in somewhere middle at the saturation point, so it will increase till it touches the boundary of saturation and linear region.
yeah, and then it will go into
Then it
linear
will
region.
start going
Huh,
to linear region and start
huh,
decreasing.
correct. So this is
Okay.
when there is no channel length modulation. Okay, here I am assuming that channel length modulation is not there, is not present. Okay, but if there is channel modulation, it may not go into linear region, it may only decrease slightly, so it may only increase slightly, and then things might still be in saturation. So if you solve some questions on that, you will be able to understand. So like the same question, if you just assume that there is some channel modulation and assume lambda and lambda p, you will be able to understand it. So I would encourage you to try it at home. So this is what I'm trying to explain here, is just to make you understand how it is important. So yeah, so now that I've explained what happens in this kind of biasing, so here you biased with a constant voltage source, right? And you saw that if suddenly VTHP decreases, then there is an issue, right? you see that things again start going out of saturation. So this is not definitely not a good way to bias it, because when you have circuits, practical circuits, their properties can change, right, with temperature, with time, with a lot of things. So definitely this is not a very good way to bias, isn't it? So from here, what do you think? How should I bias it so that it becomes very insensitive to process variations, temperature variation, all those things? How should I bias it?
Cascode configuration.
No, not cascode configuration.
Current mirror.
Yes, exactly. So that is something which was covered in your lectures also, right? So you see how this is done is, how current mirroring helps here is this. So let's say I use a current mirroring here.
Sir, in between, is my understanding correct that channel length modulation helps in maintaining the current?
No, 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 no. Sorry, that is not the that is not what I was trying to uh, explain. Okay, with channel modulation, let me see. Here, since there was no channel modulation in the in this particular case, what ended up happening was, the moment the currents have mismatch, the voltage will suddenly go to extreme, right, to an extreme value,
Yes.
right? This is very easy to see, right, from here also. You see here, what does channel modulation mean? Channel modulation means that there is some output resistance.
Yes.
So the moment there is no output resistance, the what will happen to this voltage here? It will suddenly go to minus infinity or plus infinity, right? If there is a current mismatch.
Yes.
However, so basically the moment there is a current mismatch in between two series current sources, the voltage will suddenly jump to either plus infinity or minus infinity, right? That happens when there is no when there is no output resistance. Now, if there is some output resistance here, which basically there is some resistance here, so then the current will not the because of the current mismatch, the voltage will not suddenly jump to that value, right? It will jump to some intermediate voltage, because the extra current, which is, so let's say this is R1, this is also, so this is, let's say this is some RO, this is some RO. What will happen? There is some current mismatch here, right? So now the current has an extra path, right? It can flow through here. Earlier it didn't have any path. You understand? Earlier it didn't have any path here.
Yes.
So any mismatch in current, the current what will happen is, this current is what? Current is basically the flow of charges, isn't it? So what
Yes.
will happen? Charge will start building up in here, or it will start draining from here. In this case, 1 milliampere is being demanded, and 0.25 milliampere is being supplied. So suddenly the charge here at this point will suddenly start decreasing, right? Which means that the voltage will suddenly go down to minus infinity. However, in this resistor case, so whatever is the excess current, whatever is the excess current, or whatever is the current that is being whatever is the excess current will simply flow through the resistor. Okay, and the voltage will be something like 0.75 milli into R out by 2. Got it?
Yes.
So what happens because of this resistor? Because of this resistor R output resistance is that the voltage will not suddenly jump to a very high value or very low value. It will uh, move softly to some value.
Mayank, I have a very stupid question.
No question is
Okay,
stupid.
so
So
if you please go to that diagram.
yeah, this one,
So
this one.
yeah, so if let's say the M1 is demanding 1 milliamp and
Hmm.
the M2 is supplying 0.25 milliamp,
Huh.
so the extra current which is demanded,
Hmm.
will it come from VDD through R0, or it will, how that will
Yes, it
work?
will come through VDD, from VDD through R0 if R0 is present.
Yeah, R0 is present,
Yeah,
and
so then it will
if
come from there.
okay, and if M2 is supplying more, let's say 1.25,
Huh.
and M1 is 1 milliamp, then the extra current will pass through the R through to the
Yes,
ground.
yes,
Okay,
yes.
okay, fine.
It's not a stupid question. It's a very important question. It helps you understand.
No,
Yeah,
I'm not very familiar with the
it's
analog electronics.
it's fine. I mean, as long as you understand what I'm saying here, it's fine.
Yeah.
Good. So, what I was trying to explain here is, in this condition, the current mirror. Someone said current mirror is a good way to pass. So that is what I'm saying. So see, if you use current mirror here, okay, and you use this way, so you need a bottom current source, right? And this guy has to be connected in this manner, right? So this is a current mirror. This is M3. So what is the current mirror here? This configuration is the current mirror, right? Okay. So because of the current mirror, what is going to happen now? Still, is this a good way to bias?
Mayank, I think for both you need to do, I guess, right?
Yeah. So
For
yeah, I was coming to that. I was coming to that. Yeah. So but first let me come to that. Okay, you understood, I think, but a lot of people didn't understand this. So why is this not a very good way to bias? Still, there is some problem here, right? What is the problem here?
like M2 will supply constant current, but whereas M1 might like
Yes.
extract more current or
Yes.
extract less
Yes.
current.
Exactly. Exactly. Very good. So this guy here, it has a constant current of I naught, right? And this guy will always start giving I naught current output, isn't it? However, M1, because of some change in its threshold voltage and all, it can maybe demand more or less current, right? That can happen, isn't it? So this is again not a very good way. So this I naught current has to somehow be equal to the current that M1 is demanding, isn't it? So
Yes, sir.
yeah, so I naught is the current that is, because of current mirroring, I naught is the current that is going to be supplied by M2. So somehow this I naught has to always be equal to it has to be always equal to the current that M1 is demanding, right? So somehow this I naught has to track the current that M1 is demanding, isn't it? So how will that happen? You already have something, right? So simply connect it like this. Simply connect it in this manner. So now tell me what will happen. What can you say about the current in M4? What can you say about the current in M4? So current in M4 has to be equal to M1, right? I mean, if channel modulation is not present anywhere, so is this going to happen or not? IM4 has to be equal to IM1. Is that correct or not?
Yes.
Yes.
Yes, correct. And because of this, if IM4 is equal to IM1, right? And IM4 is the current that is going to flow through here. So how much is the current that is going to flow through here? This is also going to be IM4, right?
Yes.
And IM4 is now now we can say that IM4 is equal to IM1. So this will take care of all the process and temperature variations, isn't it? In spite of, if even if something changes, even if the threshold voltage changes somewhere, it doesn't matter, right?
Mayank,
Huh?
can you explain once again this when you have attached
Okay, so
this M4?
okay, so earlier I did this, right? So this was some current I naught, correct? And because
Yes,
of current
yes.
mirroring, if I naught flows here, same current I naught will go to will flow from this guy, right?
Yes.
But I naught still cannot be ensured to be always equal to Im1, right? Because see, this will always be I naught. That is, there is no doubt. This will always be I naught. However, this Im1 can sometimes become equal to can sometimes become unequal to I naught, right? Because
Yes.
the current Im1 is dependent upon the bias of Vb1, right? And and the threshold voltages of M1 and all, right? So this can sometimes happen that Im1 is not equal to I naught, isn't it? So to make
Yes.
sure that Im1 is always equal to this current that is flowing through this guy. So Im1 is always equal to Im2. For to make sure that happens, what will you do? This I naught has to also be equal to Im1, right?
Yes.
Got it? So for that only, I made sure that this is done in this manner. When you do this, when you connect the MOSFET here like this, so what is going to happen is the current in M4 is now going to be equal to current in M1, right? I mean the gate voltage of both are same, right?
Yes, but okay. Yes, yes.
What
Gate
is the
and
problem?
source. Okay. Like in okay, I was thinking like current biasing. There will be that one like short circuit and one more current source.
No, no, this is the way. Okay.
Okay. Yes.
So if you have now they are same currents, right? Im4 and Im1 will be exactly same. Correct.
Because gate and source are of same
Same
voltage.
voltage, yes. And I have assumed channel modulation is not present. So this will be exactly same. Im4 and Im1 will be exactly same to each other. And Im4 is also the current that is flowing through M3. Okay. And that same current M3, that same current is also going to flow through M2. So Im4 is equal to Im3 is sorry, and Im1, and this is in turn equal to Im2, isn't it? So
Which means like M4 is setting the current in the left branch and here M1 is setting the current in the right branch.
yes, you can say that. Yes,
Okay.
yes. So this actually is now ensured, right? Im1 is always equal to Im2. That is ensured. So this is a good way to bias, right? Because in spite of, even if there are parameter variations, like if the threshold voltage changes somewhere, it doesn't matter. It will always be this particular condition will always be respected, right? Im1 will always be equal to Im2. It doesn't matter even if the threshold voltage increases, decreases, it doesn't matter. Correct?
Okay.
Yes. So this is what I wanted to explain in this first question. So now you should be able to appreciate why we use current mirroring and all, right? Now you should be able to appreciate that.
Yes, like current mirror, like one question, current mirror biasing ensures that there will be in saturation and constant current
So basically,
flows.
current mirroring is what? What do you see when you see in a mirror? When you look in the mirror, what do you see? You see yourself,
S-
right?
Same copy.
Exactly same copy, right? However you move, exactly the same manner, your copy in the mirror also moves, isn't it? So this is what is being. This is how the name of this current mirror came into being. So basically, the thing is that however this transistor moves, I mean, in whatever way this transistor moves, exactly the same manner this will also move. Okay. So they try to mimic each other. So because of that, uh, this transistor here, if there is some change in the threshold voltage and all, anything, if there is any change here, in the same manner this will also respond. The way in whatever way this voltage changes, exactly same with this voltage will also change, and the overall current will remain same in both the branches. So that is how the name comes. So think about it, you will be able to understand it. Okay. Both of them behave in the exact same manner, so that is why the name comes.
Okay, like, and here one more thing, like corresponding to M2, there should be corresponding M3 as pMOS, right? Both should be same.
Yeah, M1 should be similar to M4 and M2 should be similar to M3. Yes.
Okay, thank you, man. Thank you.
Yeah. Good. Good questions. So now some guy was asking about assignment questions. So though that person was asking about assignment question, let's see what you have. Assignment 9. Yes. What is the problem? So please unmute yourself and you can say something. You can speak. In which question you have a doubt? Someone was asking me about assignment questions, right? Vimal Raj. Yeah, so can you just unmute yourself? It is very difficult for me to keep looking into the comment section. You can unmute yourself and just say something. And be very precise. I mean, I cannot give this hints to each and every question. So you just tell me which question do you want help with. I think I have said a lot about. I mean, whatever I've covered today, that should help you in attempting the questions. I think so. But the questions here are actually. Uh, I think the questions here are actually very similar to the questions that were already done in the previous assignments. Okay, in week 876. It's just that NMOS is replaced with pMOS. That's all. Okay, first and fifth one. First and fifth. So first question is find quiescent gate voltage VGQ and voltage with an ability to decimal places. So yeah, so what is the problem here? We just have to find out what is the gate voltage VG. So write the equations, okay, current equations for pMOS, and you will be able to get it. So the current in M2, okay, there is no way to, I have no way to use my pen here, so I cannot show you. Okay, fine. So maybe I will. So you can see here M2, right? The current in M2 is going to be equal to 1 milliampere. Okay, and from there you can find out what is the voltage VG. Okay, you can find out what is the voltage VG, and because of that you will be able to then find out what is VGQ naught. Okay, and the fifth question is consider a circuit as shown in figure 2. Find quiescent gate voltage of M1. W by L M1 is 40. I know okay. So 1% voltage of M1. All right. Oh, good. What is this? This is not good. Okay, so it's a very similar question. This question is very similar to what I already explained to you, right? So this is very similar to that. You just have a voltage source, current here 1 milliampere. So how much current is going to flow through M1? The same current, right? The current that is going to flow through M1 is also going to be 1 milliampere. You have the source terminal. Okay, you have the gate terminal. So gate terminal is at 0 volts. You just need to find out what is the voltage at source. From there you will be able to find out. I think everything is fine. You'll be able to do it. I mean, is there any other doubt in this in these questions? Something which is conceptual wise. Is there any doubt somewhere?
Question number 3.
Question number three. Yeah,
Yes.
tell me.
The condition for value of C act so that circuit can act as shunt circuit.
I think it should be short circuit, I guess.
The condition to act as a shunt circuit. Undergoing is to act as a shunt circuit. Okay, so you understand it, right? It is actually short, right? You understand this point, isn't it? I mean, are you able to understand this point or not? It should be a short circuit, okay?
Okay.
It should be a short circuit. How the condition of capacitor to for it to be a short circuit. That's all.
Okay. Okay.
Okay,
Okay.
this is the same thing that you have been doing in like doing in all the assignments. It's the exact same thing that you have done in all the assignments. Just that NMOS is replaced with pMOS. Only that is the difference. Okay.
Okay.
Any other doubts? Assignment. Okay.
Like not related to assignment, but in general, like all configurations which you have seen in like with N MOSFET, right? Those all like can be realized with P.
Yes, all of them can be realized with P. Yes.
Okay. Okay.
Huh.
Excuse me, sir.
Yeah.
Sir, I had a doubt in the fifth question, sir, of the assignment. I mean, the question part.
Okay.
Sir, shouldn't the value of mu p Cox should be given here for the calculation? Just a doubt, sir. Please correct me if I'm wrong.
It is given, I think, commonly at the top of the assignment. So
Is
Yes.
it
all,
common?
yeah.
I thought it's just for the figure for the first question itself.
I think you can assume it there. Okay. If you need it, you must use it. That you must use that only. If it is not
Okay, sir.
given and you may not need it, then that's a whole different story together. Okay. Altogether. So
Okay.
if you need it, if you absolutely need it for solving this question, you should use the first that only. Okay. First of all, it should be mu p Cox. Okay. It should not be mu and Cox. That's a typo. It's a mu p
Okay, sir.
Cox.
Okay, sir. Thank you.
Yeah. Okay, so I think that is fine. So now let me come back to this one. I covered this all these things here. Good. Problem number two. So this I will not cover. This I have designed for your homework. So what I want you to do it. I want you to try it. So this question is actually a very interesting one. So this is a in the last. Okay. So Mayank, please hold on. Okay, I will come to that question. But first, let me discuss this. Okay, so this is a very common, very famous circuit. Okay, uh, do you identify it by the way? Have you seen this particular circuit somewhere?
CMOS inverter.
Yes, it's an inverter. Okay, so you generally know inverter to be used in digital circuits, right? Generally, remember them being used as in. So this is the symbol that you must remember for inverter. And if you give any step signal like this, you get inverter signal here, right? This is what you know about inverters. I think that is what you know. But you see, inverters are not only used in digital circuits. It's not only for 0 and VDD. Okay, it can also be used to process analog signals. Getting my point? So see, in digital signals you only have 0 and VDD, right? In analog signals you have lot of different intermediate states also, right? Between 0 and VDD you have all lot different places where you can have signals, correct? So inverters are not only used in digital circuits, they can also be used as amplifiers in analog circuits. So this question is supposed to motivate you to do the same only, to understand the same. So try it out on your own. Okay, this question I have designed, I'm sure that you will be able to understand it because I have discussed a lot on the previous question. This question you should be able to discuss. So first question, I think you can do it right away. So tell me, is the circuit properly biased? Do you sense any problem with the biasing here? As a hint, find the small signal gain, V out by Vi. So tell me, is this circuit properly biased? What is the point of biasing? What do you mean when we say we have biased a circuit? We have to bias a circuit. Yes, say something, please. So one guy is saying VGID. So I don't understand two words VGID. So what is that? So you can maybe speak up instead of typing on the comment section. You can speak up. So what do you mean when you say that I have to bias? When you are asked to bias a circuit, what do you understand with that by that? So when we say that we have to bias a circuit, it means that we have to basically for MOSFETs we have to make sure that the DC voltages are such that DC voltages and currents are the acceptable are of the acceptable value, so that we can get good small signal performance. Okay, so please understand that biasing is something which we do for DC. Okay, biasing has something to do with DC or at DC. Okay, and it is done to make sure that small signal parameters are what you desire. Okay, so basically a biasing circuit should not disturb the small signal performance. Getting my point? A biasing circuit should not disturb the small signal performance. So tell me something, is this circuit properly biased here? Do you suspect any problem here? Is this biased properly? Okay, fine. So let's understand this. I think you not understood biasing properly. So let's say VB is, oh, it is given as 2 volts. So this voltage is 2 volts, right? This is 2 volts, and Vi is, let's say something, let's say it is A naught or A naught. Let it is sine omega naught t. Let's say it is 1 volt sine omega naught t. That is Vi. So what is the voltage that is going to appear here?
2 volts.
Why it is not 2 volts plus 1 volt sine omega t?
Yeah, 2 volts plus minus 1 volt, basically.
No. What is 2 volt plus minus 1 volt?
So it will go up and down, right?
Yeah, so
It's
it is 2
sinusoidal.
volt 1 volt sine omega t. Are you saying this should be the one?
No,
Yes.
I am saying it will go till 3 volt and it will come down to
No.
1 volt.
So I mean, in the time domain I am asking exact expression, so it will do this
Okay,
oscillations,
okay.
right?
Yeah, 2 plus 1 volt sine omega t.
So but will it be this much?
Yes.
No.
Yes.
No, it will be only 2 volts. Why is that? It doesn't matter if there is Vi placed here. You see this voltage here, Vb, right?
Okay.
This voltage Vb here, it is directly connected at this terminal, right? It is shorted with this terminal.
Yes.
So and we know that a voltage source knows nothing. It's a king, right? In its own world, and the moment it is placed somewhere, it will try to impose its own rule. Okay, if it is shorted to some network, it will simply impose its own condition that the voltage there should be 2 volt exact, no change, isn't it?
Yes.
So the voltage here will always be 2 volts. So tell me then, in that condition, what is happening to Vi? So Vi was 1 volt sine omega naught t, right? It is also a voltage source only. But what is happening? Why is this voltage not appearing here?
Because 2 volt is
Voltage
in
drop.
parallel with that,
Right?
and yeah.
Yes. So 2 volt will always be here. Okay, 2 volt will always be here. Because of this 1 volt sine omega naught t, it will appear at this place. Okay, 1 volt sine omega t will appear here. Hmm. And because of this, there will be a current here. That current will be sinusoidal, but ultimately this voltage at right at this point will always be 2 volts. Okay, that is being enforced by the this biasing voltage only. So, so now tell me, so okay, a moment ago I just said that your biasing circuit should never disturb your small signal operations, right? But in this case, you can see that uh, the voltage source that we used to bias it completely, what can I say? Completely eliminated the small signal, right? At this place, there is no signal is not even going in, right?
Yes. Yes.
So something is definitely wrong with the biasing. So what is wrong with the biasing?
So small signal should be in series with the VB.
That is one way. That is one way. But let's say I cannot do that because I don't have access to both the terminals of small signal. Okay, let's say I cannot do that. So how will I do that? So this is very easy, na? You have already learned
You
it.
can reduce RS, I guess.
So what will happen? Okay, oh, you are saying this. Okay, let's say I reduced RS, and so this is the extreme condition for reducing RS, right? I shorted them. So tell me what is going to happen. I think I spoke a lot on this, right? What is this condition? You are trying to short two voltage sources. What is going to happen? Yes, Nikhil.
It might go to infinity. It might increase voltage.
The voltage will not go to infinity. The current inside this, in this voltage sources, will suddenly increase or decrease, right? It's not a good
Yes.
thing. It's not. It's not advice. It's not a good thing at all. You not do that. So what should I do? So this I think has already been covered in the lecture. So tell me, you have been seeing this for quite some time now. Now, what should I do? I do this. Okay. So let's see if you remember suddenly. This you have already done. So I'll do something and tell me whether you remember it or not. Do you remember this? Huh? Do you
The
remember?
coupling.
Yes, this is a coupling capacitor, okay? And this is how we put it, right? I mean, the whole reason of putting this coupling capacitor was to make sure that the DC bias does not disturb the small signal performance, okay? Now for the DC, you can see that this capacitor remains open, right? So in the DC picture, this will not even be present, right? Only this is going this way. In the DC, this voltage VB is directly appearing here, right? Isn't it?
Yes, capacitor will be open.
And in the AC case, where at the small signal case, what is going to happen? This voltage can be assumed to be, I mean, this voltage will be there, okay, but in the small signal, this voltage is shorted, right? I assume that this voltage is shorted, so this is not there. So what will happen? And this capacitor will be assumed to be shorted. So this signal can go through like this, isn't it? Is that point clear?
Yes, sir.
Yeah. So please keep revising, okay, and keep thinking. about why we did something which we did. This course is supposed to be a design course, right? It is analog VLSI design. It's not supposed to only, you're not supposed to only just solve the questions and that's all. You also need to understand why we made certain design decisions. Okay, it's a design course. This course is supposed to evolve you as a designer. So you need to also start thinking in terms of why you took a certain decision, why you placed certain component in the circuit. Okay, as designers. Fine. So okay, so now that I solved this, try to also think. Okay, now tell me, is something wrong at the output side also in terms of biasing?
Yes, sir.
What is wrong?
Like with respect to
Again,
MMOS.
capacitors. Right?
Exactly. We need to add a capacitor also at the output side, because why is that capacitance required? If this capacitor is not there, what will happen? So let's say this capacitor is not there and it is directly shorted. What is going to happen?
Bias current will flow into RL.
Yes, exactly. Let's say this voltage is 2 volts, a lot of bias current will flow here, right? Not good. I don't know how
RL
fast
will
it.
load also, right?
Yes,
RL
RL
will load.
RL will load anyway. In the AC picture also, in the small signal picture also, RL will load, but RL will also load the DC picture. So that is what the other guy meant when he said that this will start taking DC current or bias current. Not good. So that is why I need to add a capacitor here also. So let's call it CC. Okay. So this is the complete biasing circuit. So now that we have done the first part, so okay, this is, I would like you to try the other parts yourself. Okay, so try the other parts yourself and try to, yeah, try to come with answers the next session that we meet. Okay, guys, thank you. So that much would be all from me today. So we'll meet again next Tuesday. Okay.
Hello.
Yeah.
One question, like we added one the output cap there to prevent the output current flow. Like what could be the typical value of CC? Like if I were to say like in picofarad or like femtofarad,
No,
like what could be the
picofarad.
like from design point of view?
No, no. It actually depends upon which frequency you are interested, or what frequency operations you are interested in. It can be femtofarads also. It can be in picofarads also. So that's what. Now, I mean, all the assignments that you have solved, you have been asked to find out what is the value of capacitor to for it to work at certain frequency, right? So they are
Yes.
very practical questions. Okay.
Sir, one basic
Huh.
clarity I want.
Yeah.
Uh, Regarding the capacitor, we are comparing the time constant with greater than 1 by omega naught
Yes.
generally.
Yes.
So we want to make the time period more than the time constant. Is it that is what is?
Yes, exactly. Yes, you're trying to make sure that time is time that you are giving your signal. In that time, uh, the capacitor voltage and all everything should settle. Okay, so that is why, that is what you're trying to achieve. Yes. Okay. Okay. So I completely forgot about Mayank's question. So he had a question week 8, assignment 8. So Mayank, are you still there? Yeah. So what was your question in assignment 8? So please unmute yourself and say something. I mean, it's very difficult for me to look at the comment section. Mayank, please unmute yourself and you can say. Okay, you have already asked. So assignment last 8th question. Question number 2. Question number 2. How did they calculate V1? What is V1? Calculate V1. So where is V1? I don't see any V1 here. So other guys who see his question, so can you help me? Where is V1? What is V1?
In while the instructor was sir is explaining that he told that V naught is equal to V1 minus like that.
So what is
That,
V1 in that solution?
V1 minus
Where is V1? V1 is voltage of what?
VTH. V1 is equal to that like that. He has explained in that, so he might be asking about like V naught is equal to V1 V1 is V1 minus what we call as our VTH.
Okay, so
So sir has explained for two transistors.
uh,
Uh, so there he has assumed that I'm not getting that exactly.
okay,
That's what.
fine. So I think Mayank, I already see. I discussed a question like this in the last assignment. Okay, last week. Please look, go through the lectures once. Okay, I will. I'll try to look at the solution myself and I will see what you are asking here. I'm not able to understand like this right now, and the time is also going away. Okay, V1 is VGS4 plus VGS6 plus VGS4, VGS2 plus VGS6 plus VGS4. Okay, so what is the problem there? I mean, you see, I that's what now I'll go through the solution myself once, and then I'll see. I will answer you in the next session. Okay, but in the meanwhile, what you can do is go through the discussion session that we had uh, just before this. I think on Saturday I uploaded the video for that. Please go through that once and see whether that you are able to understand it or not, because I solved a question like this in the last session. Okay, so please go through that. I will also look at the solutions and then try to answer you. All right, so one guy has commented that I asked me to upload the videos just after. So yeah, so I will upload it now only. Okay, just after the session I'll be uploading it. Don't worry about that. So thank you. So I think that would be all. Time is also up. So let's meet again
Thank you, Mayank. Thank you.
next.
Thank you.
Yeah, let's meet again next Tuesday. Thank you all for joining.
Thank you. Thank you.
Yeah, thanks.